Take a look at the screen you're watching right now. The light making these images visible is produced by a mechanism that classical physics cannot explain. To make this device work, engineers had to master a hidden layer of subatomic behavior. In the classical world, pushing electricity through a material usually generates heat and unpredictable sparks. But your screen relies on electrons moving between specific, discrete energy levels to produce light, allowing for the precise control needed for digital displays. That control became possible when we replaced fragile, bulky vacuum tubes with early semiconductors. By shrinking these components down to the size of a coin, and eventually much smaller, we gained the ability to direct individual electrons. This was the foundational step. Controlling these electrons allowed us to build the integrated circuits that power everything from your laptop to the internet. But to achieve the exact logic and pure light required for today's world, we have to look past the physical wires. We have to use the rules of quantum mechanics. Inside the LEDs powering your screen is a specialized semiconductor material, often a compound called gallium nitride. This material is not a random jumble of atoms. It's an orderly, repeating structure called a crystal lattice. This rigid geometry is what tames the behavior of moving electrons. The lattice provides a predictable path, turning chaotic motion into organized flow. Establishing this perfect atomic order is the only way we can reliably predict and control how subatomic particles will behave. Within this crystal, quantum rules dictate that electrons can only exist in two distinct states. Most sit in a lower resting state called the valence band, while others jump to an upper conduction band where they can move freely. Between these two states lies the band gap. This is a zone where electrons are physically forbidden to exist. When you apply voltage to an LED, you give an electron the exact energy it needs to jump across that forbidden gap and into the upper band. Electrons are unstable in that upper band. They eventually plummet back down to their resting state, shedding their excess energy as they fall. Because the band gap is a fixed distance, that energy is released as a precise photon of light. The size of that gap determines the color we see. A larger gap produces a shorter wavelength, like blue, while a smaller gap produces a longer wavelength, like red. The visible color radiating from any LED is the physical manifestation of that microscopic quantum distance. Scientists effectively program the color of our screens by mixing elements like gallium and indium. By adjusting the material's composition, they set the exact size of the band gap. This requires the foundational math of quantum theory. We have to calculate the allowed electron transitions before the hardware is ever built. These abstract theories are then verified in the lab. Engineers grow these semiconductor crystals layer by layer, testing them to ensure they meet the precision required for modern electronics. When you turn on your screen, the continuous voltage causes this jump and drop cycle to happen billions of times every second, creating a glow that meets strict industry standards for reliability. The same quantum principles once confined to theoretical laboratories are now active inside your device. Every pixel you see is a direct application of subatomic physics, shining back at you with every frame.